All right, so this is like the first video on the truth tree method. So I'm just gonna wing it and see where it goes. Gonna try to remember what Professor Sundell taught us this past semester. So the truth tree method is closely tied in with truth tables. So I really like the conditional for some reason, so I'm gonna start off with that one. So we have Q, yeah, P and Q. So 1, 1, 1, 0, 0, 0, 1, 0. So here, what it takes the conditional to be true is either a false antecedent or a true consequence. And if you remember from that introduction, you can, like, in that introduction, if P then Q is somewhat equal to not P or Q. And that's kind of what's at play here. So you write out the rule for like the semantic clause rule. I don't remember what it's called, but it's like the rule for how to determine whether this is true or not, as this: the value of P then Q, this conditional, is true if and only if the value of P is false or the value of Q is true. And then again, truth tree method, this translates to this. And since again, it's like one of these two has to be true, so you have, there's a split in the road, you know. So it's either not P or it's Q. And then this is the same for this here. So not P or Q. It's either not P or Q. And this, with this, let's just see how it works for the disjunction. So you have P, you have Q. 1, 1, 1, 0, 0, 1, 0, 0. So again, the value of this disjunction is true if and only if the value of P is true or the value of Q is true. And of course, it's also like it's also the case that like both are true, in which case it'll just be true. So because this is an or statement, and anytime you see like a statement that, you know, it's either this or that for it to be true, you branch. So P or Q. But then you also have the conjunct, so which works a bit differently. So with this, it's value of the conjunct P and Q is true if and only if the value of P is true and the value of, hold on, my bad, Q is true. And since this is an and statement, you stack them. So P and Q, P, Q. Now the biconditionals, it's kind of a mixture of both of these. You just put these two and just, you know, squash them together. So the value of P or Q was 1, again, in both of these two instances here. So if the value of, okay, so if and only if the value of P is 1 and the value of Q is 1, or the value of P is 0 and the value of Q is 0. But since this is both like or and, you have this, so but now there's like something like a negated, what do you do with negate and conditional, or a negated conjunct? Oh, sorry, bad. So just go to the truth tables on both of these. So for a conditional to be false, it's only false in one state, one instance. And likewise, a conditional is false in 3 statements, but for these, it has to have at least one false conjunct to be false. For the conditional, it's false if and only if the value of P is true and the value of Q is false. And for the conjunction, it's if the value of P is false or the value of Q is false. So that means that, so here, it's an AND statement. So a true condition, the true antecedent and a false consequence. And for the conjunction, since it's our statement, both of them are false, that is again for the disjunction, it's only false in one instance, so you and both of them have to be false. So in the biconditionals, again, false in 2 instances. So how'd you write that out? It's P, Q, not P, Q. So that's like the rules of the branching and stacking rules. So remember, when it's in or, you have to decide which path you have to take. If it's and, you're just on like the same path, you know. But I'm trying to like find out how to articulate what I want to say next. So the like tree method works is that you take an argument. So let's do a simple monens ponens. Then you and you basically turn it into like a set. So, but not just any regular set, you negate the conclusion. So this is an argument with true premises in a false conclusion. And if it's consistent, that is, if there's no contradictions found in this set, then the argument is invalid. And if there is a contradiction, then it's valid. Because you can't, like, if there's a contradiction, you can't find a counterexample. Well, if there is, if it's consistent, then like whatever appears on the tree is a counterexample. I feel like I'm not explaining it well, but I'll show you in a minute when I do an invalid form of this. So negate the conclusion. It's no longer an argument, so it's rather a set. So the rule for inconditional is you split false antecedent, and there's a contradiction here with this one. If then a true conclusion, again, a contradiction there with that. So it's valid since you can't find a counterexample. But then how about this form? Not P and not Q. So you take it, you write it out, you negate the conclusion, and you can get rid of the double negative. I do just because I like I just don't like having double negations. But so true, wait, false antecedent in a true conclusion. There's no contradictions here. It's consistent. So the counterexample would be this. And that. So this is your counterexample, which is also back on the table. This one, the third line on truth table. So I'll do one more of these problems, and then I'll do a semantic proof. So let's do other other form from natural deduction, which is the purely purely hypothetical syllogism. So you turn this into a set, negate the main operator. So this would be this. Not P, and there's Q. This is a contradiction. Actually, no, this is the contradiction. And then it's you branch to this one. So then it's not Q. This is a contradiction. Then it's R. This is the contradiction. So this is a valid form. And now for the semantic proof, I'm just gonna do modern indirect proof. So I'm gonna show you how that is. It's you assume the conclusion is false, and if you find a contradiction, it means it's valid, and I'll show you how that works. And then I'll do on another video the direct proofs. So let's do again modern opponents because it's easiest in my opinion. So this is how you do semantic proof. So you assume for reductio that this argument does not entail the conclusion. So basically what you want to do now is like think through this. So the value, okay, so that means the value of that means that there is an arbitrary interpretation such that the value of this conditional is true, the value of P is true, and the value of Q is false. And we know by the semantic clause, so by the semantic clause of the conditional, this conditional is true if and only if the antecedent is false, or if the conclusion is true. But since the antecedent is true, that means that the consequence also has to be true, which leads to a contradiction. Leads to a contradiction. Since here we assumed it was false, and here we're saying it has to be true, because this conditional is true. So then you can conclude, so actually probably, let me write it out in a kind of more sophisticated way. Since the assumption in Q P does not entail Q, led to a contradiction. That means that entails Q. Even here, I probably should have written it somewhat betterly and be like, it leads to a contradiction. Like, what I mean by that, it's I should have, in the actual semantic proof, wrote something like, since we assumed the value of Q to be false, and the value of, basically what I'm saying is, like, just write out here how, like, we said this is true and this is true, but then this can't be false if this is true, and this is if both of these two are true, because of this kind of like sloppy at the end, but like I hope someone like can understand what I'm trying to communicate with that. Yeah, this is like the beginnings, so like introduction to the truth tree method, plus like the semantic clause. That's my class, my bad. The semantic proof, but indirect semantic proof. Next time I'll do direct semantic proof, and I'll also do the truth tree method for predicate logic. And I'll put some problems in the description for you to like practice on. So yeah, peace.